Thank you. It's very kind of you. As is already evident, I'll talk about quantum weak coin flipping. This is a joint work with Jérémie Roland and Chrysoula Vlachou. So let's get started. I'm having some trouble with the slides. Okay, cool. So I'll basically start with a 4-slide summary so you can get the message sufficiently early on. Right. So imagine Alice is in Munich and Bob is in Brussels, because why not? And the travel has now been restricted. And for some reason, they want to flip a coin. Okay. And they want to do it by exchanging messages. So for concreteness, let's imagine that heads means that Alice gets to keep a disputed object, such as a fancy car. And tails means Bob. Oops, did I mess it up? Okay, heads means Alice gets and tails means Bob gets. That's not so important. Okay, so basically the problem of who gets to keep the car, more formally, two players who wish to agree on a random bit remotely without trusting each other is what is called coin flipping. Now, if we add the extra assumption that both players actually want the car, which is not a very hard thing to imagine, then the problem becomes weak coin flipping. And one might wonder why this is an assumption. Well, it's an assumption because it's possible that, for example, Alice has decided that she's not going to use petrol burning vehicles at all. And Alice is unaware of this. So she doesn't want to give Bob the satisfaction either way. So this is, I hope that kind of makes sense. All right. I must also say that to contrast weak coin flipping from the coin flipping problem, the coin flipping problem is also called strong coin flipping. Okay. Different protocols offer different levels of security. The main figure of merit for a coin flipping protocol that we consider is called bias. And this basically quantifies how much a cheating player can bias the outcome towards their desired value. So a 0 basically means that the protocol is perfectly secure, and a half means it's completely compromised. And why a half we'll see a little later. Okay, so consider any protocol where classical messages are exchanged. That is, the messages don't use any kind of quantum effects. And in this case, it can be shown that unless one is willing to make further assumptions, the bias would be half. In the quantum case, you exchange quantum messages, and the bias has a more interesting story. So for example, for strong coin flipping, it was shown that it cannot be done with almost zero bias or anything close to zero bias because the bias was was shown to be lower bounded by Kitaev. For weak coin flipping, in a breakthrough result, Mochon, it's Mochon, I think, established in 2007 that the bias can be made arbitrarily small. So it was an existence proof that there should exist some protocol which can do this, but this was not an explicit protocol. And this proof was really long, and it was later simplified by Hardness, Shayuk, Gans, Kednidis, and Magnin. As far as protocols are concerned, the best known until recently was, again, due to Mochon in 2005, in 2005, it had a bias of 1/6. This was improved to 1/10 in, I think, 2019 by ARW. And so that's me with Jérémie Roland and Stefan Weiss. And a numerical algorithm was proposed for constructing protocols with arbitrarily small bias. And the algorithm works. So it's okay, let me not say much further, but the trouble basically was that the status of weak coin flipping was still in limbo, right? Is it solved or is it not solved? And this is what we address in this work. We show that one can actually construct analytic solutions to weak coin flipping. So that is kind of the 4-slide summary of what we were able to do and contribute in this direction. Okay, now let me try to motivate the problem in a slightly larger context. So, consider secure computations. This is a very broad, it's a very powerful set of functionality in cryptography, where what we are saying is that there are a bunch of players who have some private inputs. They do not trust each other, and they still want to be able to jointly evaluate a function which depends on each of these inputs. And the players do not want to leak out any information about their input. And this functionality allows them to do it. So secure function evaluation basically does this. And in cryptography, classical cryptography, it is known that oblivious transfer that's a cryptographic primitive, which was also the subject of a plenary talk by Grio and Bartusek. I think I'm not saying their names right, but okay, I am sorry for that. Okay, so it was shown that in oblivious transfer, I'm sorry, is known to be universal for secure computation. And we know that bit commitment is weaker. And so this is all classical. So quantumly, it was shown that bit commitment with some extra assumptions can actually imply oblivious transfer. So that was very nice. But bit commitment itself was shown to be impossible in the quantum setting. And by impossible, I mean without making further assumptions, and you cannot do it perfectly. So imperfect bit commitment with like relaxed security parameters are possible. So the question was, because key distribution was a task that could be done, so people were wondering if there's anything which is weaker than this that can be done with information theoretic security, and coin flipping was one such possibility. And this also we saw was not possible. K-type showed that the bias is lower bounded, and so weak coin flipping was the next candidate. So basically, it's one of the strongest, or at least as far as I know, it is the strongest cryptographic primitive in this setting that can actually be done quantumly, while classically it's impossible without making extra assumptions. I must also mention that it's been shown that weak coin flipping can be used to do strong coin flipping optimally. Of course, it will necessarily be imperfect, and also bit commitment. These were shown by Kerenidis and Shari. Okay, so that was the overall motivation in terms of the practical application. Otherwise, also the problem is actually very simple to state, and it ends up having a very rich structure to it, which is interesting by itself. And also, there's this physical perspective to it, I suppose, that so basically it's a task of distributing entanglement, and you have to do it in a way that when both players are honest, they get like an entangled state, and when only one is honest and the other is cheating, the state is a maximally mixed state. So yeah, so I think even by itself it has some value. Okay, so now let's look at the problem in a little bit more detail. So I'll call a player honest that actually follows the protocol exactly. And when both players are honest, we want the protocol to function correctly. That is, both players should agree on the output and get the outputs with equal probability. When Alice cheats and Bob is honest, Alice can bias the output towards her desired value, and we want Alice to, so we want to protect the honest player, which is Bob in this case, and vice versa. And we don't consider the case where both players are cheating. This is independent of the protocol, but might involve some Nash equilibrium-like things, which we do not consider here. Okay, so the bias of a protocol is basically the smallest number epsilon, such that neither player can bias the outcome towards their desired value with probability more than half plus epsilon. Okay, so let's try to make this a little bit clear by restricting ourselves to weak coin flipping and introducing some notation. So when both players are honest, I denote the probabilities of them winning as PA, PB. When Alice is honest and Alice is cheating and Bob is honest, and the probability that Alice wins is given by P star A, and conversely, when Bob is cheating, it's given by P star B, probability that he wins. The bias then in that case is just the smallest epsilon, such that P star A, P star B are bounded by half plus epsilon. And epsilon is clearly between 0 and half. Okay, so let's consider a very simple protocol, and protocol is the following. So Alice flips a coin and declares the outcome to Bob. So in this case, when both players are honest, the probability that Alice wins is going to be half, and that of Bob is also going to be half. When Alice cheats, it's not hard to, it's very easy to see actually. A moment's reflection makes it clear that Alice can just lie, so she can win with certainty. However, when Bob cheats, he cannot do anything according to the protocol. He just has to accept whatever Alice says, and therefore the cheating probability for Bob is going to be half. And the bias in this case is clearly half. Okay, so that was a very, very quick description of the problem and some examples to get some intuition. Okay, so there are three equivalent formalisms which were introduced by Kitaev to discuss to understand and solve the coin flipping problem. The first of these is called, I should do it a little bit slowly. Okay, so the first one is the description of a protocol, and that uses STP duality. The second is called a time-dependent point game, and the third is called a time-independent point game. So don't worry, I'll make them clear gradually. The important thing here to note is that all of these are equivalent, and the last step is still only known to be numerical at best, that you can convert time-dependent point game into a protocol. So there's an algorithm that can do it, but we don't know how to do it analytically in general. Okay, so let's start with the protocol and certificate. So here, basically, we again consider the unitary description. So you have Alice's register, a message register, and Bob's register, and the message register goes back and forth. And what we want to do is we want to write the probability that if Alice applies her registers, her unitaries, exactly, and we optimize over all of Bob's cheating strategy, then it turns out that you can write P star A, that is the probability of, you can write P star B as an STP, where P star B is the maximum probability that with which Alice accepts that Bob is 1. And similarly for P star A, where we assume Bob applies his operations exactly, and we optimize over all possible strategies of Alice. And this is how we write P star A. So it's not very hard to write this down. What is nice is that once we take the dual, we can actually find a bound on the cheating probabilities. And this gives us and there's strong duality. So one can also find the cheating strategy. So this is basically, this is not very hard to do, but this is the first step. Okay. Now let's move to point games. So a point game is very interesting because it's just a sequence of points in a frame or on a plane, if you like. And you have to start with 2 points with location 0, 1, and 1, 0. And you have to end with a single point with location alpha, beta with all the weight. And you have to follow valid moves. I'll explain them in a minute. But the claim is that if you do follow the valid moves, then the final coordinate of the point, the coordinates of the final point encode the bias. So it basically upper bounds the bias of Alice and Bob. Okay. So now let's look at some examples of the valid moves. So if you're going from a bunch of points to a single point, then we can put the final point at the average location, but not closer. If you're splitting one point into multiple points, we must preserve the harmonic average, so we can't get closer. And we can always increase the coordinate of a point. Okay. I must also introduce this little notation I'm using, which basically says that the coordinate I write in these square bracket-like things, and the weight associated with the points I write outside. And also I use the subscript G for initial points and H for final points. And this will become useful later, so I just wanted to point it out. Okay, so with this, we can actually already do something non-trivial. But before that, I'm sorry, I forgot. I should mention that in general, so what I showed you were some examples of valid moves, but there are more general valid moves. So if you go from, say, 3 points to 2 points, then the condition that you have to satisfy is that for each lambda, you have to have this inequality. You must ensure that this inequality holds. Okay, so time-dependent. So one can actually construct a very simple time-dependent point game by using these rules. So for example, you raise 1 point because you have to start with a single point, and then you merge the 2 points, and you obtain a single point. Right? And they should already look familiar because this is essentially saying that the cheating probability for Alice is 1 and that for Bob is half. And this is essentially the flip and declare protocol, right, that we saw at the beginning. So this is very trivial, but we can make it non-trivial by using the split, right? We didn't use the split. So it turns out that if you use one split and we can arrange the weights, so you start with the split, you raise, you merge, and you merge again, you end up with these coordinates. And it turns out this was actually a result which was published in PRL, so it was very highly non-trivial, but in this formalism, it becomes kind of trivial. The question is now if you have more splits, so if you have a sequence of splits, and then it can be shown that the best you can do is essentially 1 by 6. And this was like the best known protocol until 2018. Okay, so that completed our description of point games. Let's look at time-independent point games. I'm not going to describe them in a lot of detail. All I'll say is that we allow negative weights. And what this does is it allows us to consider only 2 functions instead of a sequence of frames. And these functions satisfy properties similar to the equations I'd written earlier. Okay, and the claim here is that for every time-independent point game, you can actually construct a time-dependent point game with the exact same last frame. Okay, why I told you this is basically because it is in this last framework that Mochon constructed his time-independent point games, which actually give the final protocol, which show that. Okay, let me rephrase it. So it is in this framework that Mochon constructs a family of time-independent point games with bias which approaches 1 by 4k plus 2, where k is just the number of points that appear in this line, if you like. So basically, it's a rung of the ladder that he calls these points a ladder. Okay, so it's clear that as k gets larger and larger, you can make epsilon arbitrarily small. And so this was his proof for making, showing that coin flipping is actually possible. Okay, so I need to introduce a few more things. So the notation that I'd introduced earlier with the square bracket, one can actually think of this as basically just a Kronecker delta. And so in that sense, what we're saying...
Sorry if you don't mind me asking, I might have missed this, but are point games in one-to-one correspondence with protocols, or do they just give like a lower bound?
Right, so they're normally many to one, but for a given point game, you can construct at least a protocol. So this is guaranteed, just that the explicit construction is not a priori known.
Oh, I see. Okay, thanks.
Of course. Thank you for the question. Right. So here, G and H are just finitely supported functions, and you're going from G to H. So this is just a notation. Why I introduce this is basically because one can take the difference of H and G, and then have another finitely supported function and say that this function is a valid function if and only if H to G is a valid move. Okay, and I'm not showing you some details about what happens when they overlap, but okay, that's not so important for the moment. Okay, so now let me define something called an F assignment. So an F assignment is basically defined using a bunch of coordinates. So you have x1 to xn, and you need a polynomial of at most n-2 degree, where n is the number of points. And it has to satisfy this condition that f of minus lambda is positive for all lambda. So an F assignment is basically going to specify a finitely supported function using this formula that has been written, and we pull out the positive part in H and the negative part in G. Okay, and this one can actually see what it would look like as a quick illustration. So f is this little function here, and these are some of the points. And so you're going from one set of points to another set of points. So this basically specifies how you construct the move. And this is nice because Mochon essentially proved that all F assignments are actually valid functions. And in fact, Mochon's point game, other than a split at the beginning and some merges at the end, they essentially just use this F assignment. Okay, and so our objective, as will become clear in a moment, is basically to find a way of constructing unitaries corresponding to these F assignments. Okay, so let me quickly summarize. I described the protocol framework. I described the time-dependent point game framework, where you start with one frame and you go to a single point. And I described the time-independent point game framework. And it's formalism. I confused the words formalism and framework, so forgive me. And it's in the last formalism that Mochon introduced his proof that point games with arbitrarily low bias exist. I'm sorry, all of this has to be done because otherwise what I've done doesn't really make sense. Okay, so this is what was there. One last thing I have to explain. Oh, I'm already running out of time. Okay, one last thing I have to explain is that if you consider one step of a time-dependent point game, then it was shown that the unitary corresponding to this is going to look something like this. So there would be a protocol in which there's Alice's register, a message register, and Bob's register. There would be some standard unitaries and one non-trivial unitary. And this non-trivial unitary is going to depend on the coordinates and the weights of the initial and final points. And how that depends on the coordinates and weights is as follows. So you have a matrix xh, xg, which encodes the coordinates. Here, h and g are basically just the bases. So it's basically, this is just spanning an orthonormal basis. It's not spanning, it is an orthonormal basis, I'm sorry. And V and W encode the probability weights associated with the initial and final points. So the claim is that if you can find a U, this blue U, which satisfies these two things, that it sends V to W and it satisfies this matrix inequality, then one can actually construct this U non-trivial and then thereby construct this protocol. And then the claim is that this protocol is going to have the exact same bias as the point game, the coordinate of the point game. Okay, so that is like overall what we're trying to do. Now some very quick unitaries. So for the split and the merge, it was shown that in the same article, it was shown that this unitary, so you send W to V and V to W and do identity on everything else, actually suffices. It works like it should. And the nice thing with this is you can already convert the 1/6 point game into a protocol. So this is cool. And to go beyond, we actually need to do it for the F assignments, right? This is what I mentioned. So recall that the F assignment looks something like this. And the aim for us is to solve an F assignment. And by solve, what I mean is I want to find this unitary which satisfies V to W, like it has to send V to W, but more importantly, it has to satisfy this matrix inequality. We'll consider some special cases. So what I'll look at is the case where fx is basically just a monomial. So it's minus x to the q. And I'll say something is a balanced monomial when the number of negative points and the number of positive points are identical. And I'll call it unbalanced otherwise. And finally, I'll call something aligned if the degree of f is an even number. Okay. Otherwise, I'll call it misaligned. These are not extremely important. The only important thing is that there are 4 kinds of monomial assignments that are important, and I'll show you how one of them, or one particular, can be solved. I'll also have to say something about an effective solution. So suppose that you have a finitely supported function t, and you write it as the sum of finitely supported functions, where it is the case that all of these are valid functions. Okay, so you write a valid function as a sum of valid functions. Then I'll say that T is an effective solution if for each Ti I can find a solution. So basically, if I can find a unitary matrix for each of the Ti's, then I will say T has a solution. And it's not hard to show that a time-independent point game can be converted into an explicit protocol if each valid function that it uses admits an effective solution, which is to say that if each valid function can be broken into some other valid functions, and if you can solve each of the constituent valid functions, then you would say the initial valid function then you can use the initial valid function to convert the point game, time-independent point game, into an explicit protocol. Okay, so the idea is, as it's probably already clear, that you want to break an F assignment into a bunch of valid functions, and it turns out that one can break it into a sum of monomials, and each monomial actually is a valid assignment. It's not very hard to see this. And the thing is that if you can solve each monomial assignment, so this is kind of why I showed that there are 4 categories. So if you can show the valid assignments, if you can solve the valid assignments, then we are sort of done. Right. Okay, and of course, we already know that the splits and merges can be handled using blinkered unitaries. Okay, so shoot. Sorry, yeah, the slides were not advancing. The non-trivial part then is basically just to solve the monomial assignment. So let me give you the solution. So we consider the case where M is 2B, so it's an aligned monomial assignment. Then I write the assignment T, and I pull out some X's, XH, and XG, and keep the remaining things. So basically, I had the F assignment, and I write the F assignment in this particular form. And using this, I can define the matrix XH and XG, essentially like I had done before, and also W and V, which encode the coordinates. And the claim is that this unitary that I've written over here solves the F assignment, the monomial assignment. I'm sorry. Okay, so of course, it's not going to be clear why it works, and I'll unpack it in a moment, but it's just to say that the solution can actually be expressed in a single slide, so that's kind of nice. Okay, so let's try to get some intuition about it. So I take the special case when B is 0. And in that case, let's draw a little picture. So you have, say, n points, and you're going to another set of n points, and the weights are determined by Mochon's assignment for the monomial with 0 degree. So we send B to W. This is essentially a necessity. And then for the next step, well, one can say, okay, we have a matrix which contains something, and we have a vector. So let's multiply them and send it to the other one. That's reasonable. And remove the components along the previous direction, and then do it with higher powers and so on. It should be n-1, so forgive me for this, but yeah. Okay, so let's do this and take the Hermitian conjugate. And it turns out that this unitary is actually what I had written earlier, and this unitary does what is required to be done. And I can also give you a bit of intuition as to why that works. So recall that the unitary U had to be such that this matrix inequality was satisfied, and we already saw that UV goes to W by construction. So then one can write the difference matrix as D. And so before we see what D does, we have these 2 claims, and essentially these are the only 2 properties of Mochon's F assignments that we use. And the properties are as follows. So x to the power k is 0. So what that means is that if you take the average of the coordinates finally and subtract it from average of the coordinates initially raised to some power L, then this expectation is 0 for all powers of, so for all k, basically all powers of x, which are from 0 to 2n minus 2. And when it's 2n minus 1, then we know that it's strictly positive. So the assertion is then that this D, this difference matrix, when you write it in a certain basis, you can actually show that all the terms disappear due to this observation that x to the k is 0. And the last term, it turns out one can, okay, so I'll probably not explain the details, but one can show that this last term is essentially this little x to the 2n minus 1, and this is strictly positive. And so thereby you conclude that the condition is satisfied. Right. I think I can quickly summarize because I'm almost out of time. So we found exact solutions, which are relatively simple unitaries, which constitute weak coin flipping protocols with vanishing bias. And it also circumvents a certain technical conic duality argument, which was used in the numerical algorithm earlier and for the proof of existence. So that kind of makes the existence proof also neater because you found a solution. Okay, so there are a bunch of open questions. So one of them is that when we used effective solutions instead of solutions, we actually ended up increasing the dimension because, as I said, the only measure that we were worried about is the bias of the protocol, not the resources it's using. So this increases the number of qubits you need. Another interesting thing about the qubits is that for the 1/6 protocol, one can show that you need a constant number of qubits to approach 1/6. But to approach 1/10, the number of qubits scales and it explodes. So that's not nice. But we don't know if this is just an artifact of the construction or if there's something actually deeper going on at this level. Also, it was shown by Miller in 2020 that the number of rounds that you need for approaching a bias epsilon is exponential. So this is never going to be, so there's never going to be an efficient protocol that does this, but it's still interesting to see like how the constant scale, like maybe we can do 0.01 without too many rounds, and that's kind of okay. The next question is noise robustness, which is also very interesting because we cannot use regular error correction, right? Because if you use error correction, that could possibly be exploited by the other party. So it's important to see how noise affects the bias, and there's this quantum strategies and quantum Combs formalism, which might be of interest, and we were exploring this with my co-authors at some point. We had started exploring this a little while ago. Another very interesting direction is device independence. So here we are kind of, we can maybe discuss this at the round table, but this is entirely open. We do not know if there are any lower bounds. And the best known explicit protocol has a bias of 0.336. And so we were able to push it down a little bit, but so this thing is also entirely open. I think with this, I'm almost out of time. And so thank you for your attention. And if there are any maybe quick questions, I can take them.
Thanks, Atul. So just a reminder, you can write your questions in the chat and also ask Atul at the round table after the session. I think we have maybe time for 1 or 2 questions, so I'll pick some from the Slack channel. Let's see. So Zhu Kao is asking, can the weak coin flipping be extended to more parties? For example, if the coin has n sides, like a dice.
Yes, so this actually has been studied. There was an article by Jérémie and I think they were able to do it without. So I think there's a result where using weak coin flipping, you can do die flipping because that's actually weaker. So weak coin flipping is stronger than die flipping or die rolling. But die rolling itself was done independently, solved independently as well. So that's the extent of my knowledge in that subject. I'm sorry, we can discuss it later. I can point you to the reference if you want.
Anne is asking, what is the essence of the classical impossibility of weak coin flipping, and what is the feature of quantum information that allows us to circumvent it?
Right. I don't think I have a very simple answer to this. I can discuss it at the round table. I mean, there's a technical argument because for the classical case, it becomes an LP, and for the quantum case, it becomes an STP. And there is a quantity. So the impossibility proof crucially relies on the fact that it's an LP, and the argument fails to work for an STP. But I don't have a physical understanding as to how one would explain this.
Okay, and maybe one final question. Zhu Kao is also asking, for strong coin flipping, there's a lower bound due to Kataev. Is there a construction that matches that lower bound?
Yes, so there's no direct construction. But there is a result by Kennedy and Shai that I mentioned at the beginning, which I was probably not very clear, which says that if you're given weak coin flipping, perfect weak coin flipping as a black box, then you can saturate the bound for strong coin flipping. Also for bit commitment, apparently. This can be done.
Okay, all right, thanks. Thank you very much, Atul. So maybe let's move on to the next speaker.